We all agree that this is Physics 1510.
I hope so.
Good. I'm Dr. Chabay. All this information is available in Canvas, which is what we'll use to communicate about the course. This is somewhere, James? Oh, this is Jacob. He's one of the TAs for our course. James will be back in a minute. He's the other TA. You'll see them in lab, and both James and I will have office hours up in the lab room. So who am I? I'm a physicist. This is my second year at UNT, and my first time teaching Physics 1510. My research area is actually, this is James, he's our other TA. One of the people who will help you in lab and also with homework. This is my first time teaching Physics 1510, and I'm really delighted to be here at UNT. I've taught at other places. I've taught at Carnegie Mellon and North Carolina State. But I particularly like it here at UNT. My research area has actually become focused on how people learn and understand physics. So my research area is what's called physics education research, even though I was trained as a physicist. And my interest is in constructing activities and whatnot that actually help you understand physics better. So that's, in the corner of this is Dr. Sherwood. We're doing an experiment here. We're just going to try videotaping the lectures. And if they work out okay, we'll post them online and let you know where they are so you can review lectures. So what is this course about? This course is about, this is the first semester of a 2-semester calculus-based introduction to physics for students in the sciences. So some of you are probably physics majors. Some of you are probably biochemistry majors. Some of you are chemistry majors. And we're going to be talking about how interactions between objects affect their behavior and change their behavior. So physics is about change, and we're interested in exploring both conceptually and mathematically how interactions with the surroundings make behavior of systems change. We're going to start out talking about motion and changes in motion, and then what kinds of interactions change motion, and we'll go on from there. We're going to talk a little about the structure of matter, what it's made of, how it's put together, how that affects how it interacts, and a little bit about the atomic structure of matter, some of which you know about from chemistry. And we're going to talk about energy in lots of forms, including thermal energy. It's just one kind of energy, so heat and temperature. What do you have to do well in this course? Come to class and with your brain turned on. Do the homework with your brain turned on. Homework is where you really, really learn physics. You're practicing applying things you've learned in lecture. And get help when you need it. I will set up office hours. James will have office hours. We're both going to be doing it up in room 204 upstairs. Office hours are free help sessions. So when you're struggling with something or you just have a question, drop by, ask us. Don't get stuck. This is probably not that easy to see. Let's see if we can make this any bigger. Maybe you can see it. This is a graph from last year of do you know what a scatterplot is? Yeah, it's a scatter plot. So on this axis, this is class attendance, and this is final grade in the class. And notice that there's a very strong correlation between coming to all the classes and doing well in the class. So it's not the only thing you need to do. You'll need to read the book. You'll need to do homework. But so this is an attendance sheet. Please just initial by your name. If your name isn't on here and you think it should be, please write your name at the bottom of the... Okay, homework. Homework and course grade. Okay, so this is a scatter plot. This is homework score not normalized. And that's grade in the course. Another very strong correlation. Doing homework is important. Doing homework thoughtfully is important. How did these people who got high scores on homework not do well in the course? Well, there's ways to do homework and there's ways to do homework, right? If you find all the answers online or from your friend, you may get a high homework score, but that doesn't engage you in the kind of thinking you need to do to actually be able to do these things on tests and quizzes. So there'll typically be 2 homework assignments a week. One will be labeled basics. It's the basic stuff you need to know basically to get a C in the course. You need to be able to do simple problems, to understand what equations mean, things like that. And then there'll be a more challenging one that involves actual problem solving. And we'll talk more about that later. There are, I don't know if you've seen this before, this is a thing called Bloom's Taxonomy. And it has to do with levels of knowing and understanding things. So at the bottom is just remembering stuff. So I remember the definition of something. And then a little bit higher is understanding it. I can explain what it means. Apply and analyze means I can actually use this in thinking about a real world situation. I can solve a problem using this. And not just a problem I've memorized how to do. Okay, so this is C-level stuff. This is A-level stuff. We'll be working on these things. You're not thrown to the wolves. We'll be practicing this. And in fact, we'll practice a lot in recitation. Recitations are where you work. So you practice applying on problems I give you. You practice applying what we've been doing in lecture. We'll work on making sure you got the basics, but also really on strategies for solving more complicated problems. Grades, there'll be tests, there'll be a final exam. Homework counts a lot because it's important. Attendance, both lecture and recitation count. There'll be a quiz every week, usually on Thursday. Take the quizzes seriously. Use it as a self-test. If you can't do it, it means you're not up to speed. Be due Tuesday evenings. Don't get behind. In fact, work on it a little bit during the week, every day, instead of... Okay, all this information is in the syllabus. The syllabus is in Canvas. Homework and textbook. The textbook is called Matter and Interactions. And this course is part of Access Day 1, which is a program at UNT to make sure that everybody has what they need on the first day. So Canvas. Okay, so this is the Canvas homepage for our course. If you go to modules, you'll see the syllabus and the course calendar, which lists the dates of the tests and a rough calendar of what we're going to be doing every day with associated readings, so that you can. This is a document that that explains what Access Day 1 is. Basically, the idea is that you're automatically opted into this, and if you stay opted in, then you have access to all the course materials, the ebook and the homework system on day 1, and it gets billed at a discounted price. I think it's $63, and you so you can look at this this document. To get to your homework, it isn't quite the way it says in this document. If you go to the Wiley Plus is the system that has both the ebook and the homework. If you go there, and it's actually best to do it in a new tab. That was probably a bad idea. Let's see if we can do this in a new tab. Yeah. There we go. You'll find that I'm going to go to student view here. You'll see your course. It's active. If you click on it, you'll get to your course materials. So go. Here are your assignments. You've already got one. It's due. You have 2 assignments. This is a Wiley Plus assignment. It's going to be on what we do today and on and Thursday on vectors and using vectors to represent the world. And the assignments actually include readings as well. So here's the chapter 1 reading. The other assignment will pop up at the end of this class, I think. So here are the sections of the book. So this is how you get to what you're going to need for class. This should work. It's the Access Day 1 is the first time we've done this at UNT. If it doesn't, email me, but it should. The other thing to do is in Canvas, this thing called Course Materials. Make sure that it says you are opted in to Access Day 1. It says I'm opted out, but I don't want to be opted out, so I'll opt in. You have the right to opt out, but then you're going to have to get the materials somewhere else online, and it's going to be more expensive. So this is a good deal. There's another assignment that you'll see in Canvas that I'll tell you about at the end of class. Yes?
So when I was at the bookstore talking about this, I saw your note saying come to class first, but they also told me that there's a way to upgrade it to get the physical book as well. And I just wanted to ask that question on how to get the physical book, because ebooks are not that fun sometimes when you're trying to learn something.
Okay, so I don't know that there is a way to get a physical book. You may be able, so the hardcover book is they're not printing any more of this edition because they're really moving to ebooks. You may be able to find a used copy online. Make sure it's the 4th edition. There has been a loose leaf binder version and I will, if you email me after class, I will ask our Wiley rep about that. If there's still a way to do that.
They said that there's some sort of way to upgrade this into getting a new loose leaf. That's what they
Okay, there may be. The thing I'd recommend is that for $18 you can actually get a downloadable version of the ebook that runs as a standalone thing, and then you get to keep it forever, and it means that you can highlight it, you can make notes, you can make cards for practice cards for yourself and whatnot. So if you want to, I would suggest that. But it turns out I actually like the ebook a lot, so I actually don't use the paper book, but it's your call. So email me and I'll try to find it. Other questions about this? Okay. I want to show you something else that we're going to be doing this semester. We're going to be doing physics in many different ways. We're going to be doing physics by talking about concepts. We're going to be doing physics by applying mathematics, algebra, and calculus to describe the world and make predictions about the world. We're going to be doing experiments that are the lab in this course, 1530, which is a co-requisite. You should be registered for it. Is very tightly tied to what we're doing in lecture. So the idea here is going to be that if we cover something in lecture one week, the next week we'll probably be doing something in lab related to that. Okay, so it's pretty tightly coordinated. Lab is important here. Another thing we're going to be doing, though, is a little bit of computational modeling, because this is the 21st century and all scientists use computers. Physicists use computers to make models of physical systems. Chemists use computers to design new compounds. Biochemists use computers to try to correlate DNA and protein structure. And so we're going to be 21st century physicists, and we're going to do a little bit of computational modeling. You do not need to know anything about computation to start out. We will teach you a little bit, enough so that we can work together on this. So don't freak. It might even be a little fun. And I'd just like to show you a little bit of what this might be like. So I'm going to go to a website called glowscript.org. And it wants me to sign in. And I want so now I'm going to be typing a lot of stuff that isn't going to be familiar to you. They're going to be physics ideas and computational ideas that aren't familiar to you. That's okay. Just kind of go with the flow. This is just to kind of give you a sense of the kind of thing we might be able to do as we go along. So the world is three-dimensional. You've probably noticed that. And so we want to be able to model the world. What physicists do is models of the physical world. We want to be able to model the world in 3 dimensions. It's not always useful. We can do a lot on blackboards or on pieces of paper, but it's not always completely useful to do things only in 2 dimensions. So we want to be able to work in 3 dimensions. So I'm going to tell the computer here, we're in a language called VPython, to make a sphere. And it looks like it made a sphere. How do we know it's a sphere? Well, if I use the right mouse button, I can move the camera around, and it looks like the light changes, so maybe it's a sphere. If I use the mouse wheel, I can zoom in and out. I can even zoom inside it. That's a little odd. Okay, but there's really no physics in a sphere, so what can we do with a sphere? Well, suppose we want to model a system of a ball interacting with the Earth. We'll give it a name. We'll call it ball. It's a sphere. And it's living in a 3-dimensional world, so let's put it somewhere other than the origin. Position equals a vector. Who's used vectors before? Okay, we're going to learn about vectors today. So a vector is something that has a magnitude and a direction. And we're living in 3D space, so we're often going to work with a Cartesian coordinate system where the x-axis goes to the right, the y-axis goes up, and the z-axis comes out of the board toward you. So z this is called a right-handed coordinate system because if you hold your right hand, your thumb goes in the direction of x, your first finger goes in the direction of y, and your second finger sticks out in the direction of z, and it can be oriented any old way. So in this 3D coordinate system, we'll make it -6 in the x direction, 6 in the y direction, and 0 in the z direction. And we'll give it a color that's more interesting than white. And we'll make its radius a little smaller. Okay, so that's what I've typed. Sphere, its position is a 3D vector, color is green. So a 3D vector really just gives you 3 coordinates in 3D space in this case here. And now if we run this, we now have a sphere named ball at a different location. Now it's not doing anything because the computer is dumb and doesn't know any physics, so it's our job to tell it about physics and what. So maybe we want to make the ball bounce, so let's make a floor for it to bounce on. Floor, and we'll make a box. Ack. Sorry, I violated the first rule of physics class, which is turn off your phone. So let's turn off the phone. I apologize. And we'll put the floor a little bit lower. We'll put it at 0 in the x direction, but -5 in the y direction, 0. And we'll give it a length of 20 and a width of 20 and a height of 0.5. Now we have a floor. Ball still isn't doing anything interesting. Well, in order to make it needs to have a velocity. Now velocity is also a vector quantity because it doesn't just have a magnitude, that we call speed in physics, it has a direction. So we can make a velocity vector here. We'll just call it V is a vector of 0.900, and still nothing happens. So we need to tell the computer what to do with velocity. So what we're going to do is just animate the motion by taking little steps, just like a movie frame. And we'll use the velocity to tell us how far it should go in a particular little time step. So we're just going to take little time steps. So we'll have a delta t, that's a little time step of 0.001 seconds, so a millisecond. That's not very long. And we'll start out counting with time at 0. And now we'll say we want the computer to just keep doing this over and over. So we'll say while t is less than 60 times 60, so 60 seconds in a minute, 60 minutes in an hour, less than a virtual hour here. We'll say ball dot position is ball dot position plus velocity times delta t. Now distance is speed times time, right? So a vector displacement is going to be velocity times time. And we better increment time. And now if we run this, things happen way too fast for us to slow this down. We'll say we'll do rate 500. And let's tell our ball that it should leave a trail. So we can see where it's going. And now we see that the ball, we've told the computer what to do with velocity. What velocity tells you what direction you're going, and we're taking little time steps. And so, okay, that's still a little bit boring though, because it's traveling in constant speed, and it. So what's missing? We have a model of the system. We have the ball, we have the floor, but we're missing some important piece of what's going on, right? So what would really happen? Gravity. Okay, so there's an interaction with the Earth. So we need to tell the computer how to deal with that. So you may have seen the number 9.8 assigned to a name little g. This is the magnitude of the Earth's gravitational field near the Earth's surface. It's 9.8 newtons per kilogram. And again, if this is unfamiliar, don't worry about it. Well, this is what we're going to be doing for the whole first part of the semester. And so the Earth exerts a force on the ball. I better spell it right. Okay, it's not in the x direction. It's going to be in the negative y direction. So g times the mass of the ball, 0. And the computer's going to complain because we haven't told it what the mass of the ball is. So let's make that 0.2 kilograms. And now what forces really do is they affect what's called momentum. Momentum, which for some arcane reason has the symbol P in physics, and we'll get very familiar with it quite soon, is a product, or it's approximately a product of mass times velocity. And so now what we can do is say to the computer, update the momentum of the ball by having this force act for a short time, delta t. Now we have a new velocity, which is momentum over mass. Oops, I used the symbol v, not velocity, so. It falls, and it keeps falling. We forgot to tell the computer about floors. Okay, so our model works, but we have to add a little bit. Say down here that if the y component of the ball's position is less than the y component of the floor's position, we're going to do what's called an elastic collision. It's going to squish and then go up, and so we'll just reverse the direction of the y component of the ball's momentum. And now let's see what we've got. Okay, let's make it run just a little faster. This rate command says do no more than 700 of these loops per second. Okay, so now we actually have a model of a physical system. We had to put the physics in, but the nice thing is we get to see the actual behavior of the system. We can rotate it. We can see that it's kind of going in a straight line. And we can make graphs too, of course, but we forgot to tell it that the floor ended. But you get the idea, right? So this is one of the kinds of things that we're going to be able to do. And your other homework assignment this week is a thing called Welcome to VPython. It's a little interactive tutorial. Introduces you to some of the things you can do in this. Meant to be it's not meant to be something that teaches you everything you need to know. It's a once over lightly. The idea is for you to get in there, get your hands dirty, explore, change some code, make a mistake, Okay, it's just sort of mess around. All right, so let's talk about vectors, because we're interested at the beginning of this course in motion and things that change motion. And to talk about motion, we have to be able to say where an object is at one time and where it is at another time and how long it took to get there. So we use vectors to describe that. So we're going to need, and the easiest kind of vector to think about is called a position vector. And it just tells you where something is in space relative to some origin. So we're going to need an origin. Let's make this monitor here the origin in our classroom. Okay? So the positive x-axis is going to go that way. And the positive y-axis is going to go that way. And the positive z-axis goes toward you, which means that my z-coordinate is positive or negative? Negative. Okay. So let's just think about some vectors here. So here's our origin. And here's some location in space. What do you think its coordinates are in our coordinate system? We're using SI units, so meters, kilograms, seconds. So what do you think the vector going from this origin to this location is, approximately? So 2.5 meters, that's would be which direction? X? So this, I think, is 2 meters. Let's see, we've got, yeah, 2.5 sounds, maybe 3? We'll call it 2.5 meters in the x direction. So we have 2.5. Now y. So here's our origin. What do you think about y? 0? I think it's 0. I think it's a little, yeah, maybe third of a meter, half a meter, 0.25. And in the z direction, is it 2 or negative 2? Okay, so that's the position of that of this location relative to our origin. Another word that we sometimes use when talking about positions is displacement. So in this case, we would talk about a displacement from the origin. But if we move this x over there, then there from here to there. So those are words that we use talking about. Now, vectors have units in physics. And so the units of distance are going to be meters. We're going to be working with meters. So if we imagine an arrow going from here to there, that's that vector. And we can often we call a position vector r, so we'll call this r1. To distinguish a vector from something that's not a vector, we write an arrow over it. This is an important notational convention, and if you're sloppy about it, you'll probably confuse yourself. So remember, a thing that's not a vector, so location is a vector. We talked about velocity being a vector because it's got an amount or a magnitude, but also a direction. What's a thing that's not a vector? Time is not a vector. And things that are not a vector are called scalars. It's just one number, 3, 2 times 10 to the minus 7, 3 seconds, 2 times 10 to the minus 7 Kelvin, minus 6 Kelvin, a temperature. That's a very small temperature. Okay, how far away is that point from this location? How would we get the distance? If we know its location, how do we figure out how far away it is? Well, what would we do with a sine and a cosine? We could use the Pythagorean theorem. We have 3 dimensions here. So the distance is going to be is going to be 2.5 squared plus 0.3 squared plus minus 2 squared. We take the square root of that, meters. And what is that? Let's ask the computer to do it for us. Let's make, or so no, probably it would help to be able to see what I'm doing, wouldn't it? So we're using a language called Python square root. It's a lot like your calculator, the notation. So we want 2.5. The only thing that's really different is that we use 2 asterisks to square it, plus 0.3 squared plus minus 2 squared. And if we, whoops. Okay, so it's about 3.21 meters. What we did is we calculated what's called the magnitude of this vector, the size. Okay? And the way we do the notation for that magnitude we use the absolute value symbol, but when you wrap it around a vector instead of a scalar, it means magnitude. And what it means is take the square root of the sum, and that's the magnitude of that vector. Okay. Could we make a vector that is in the same direction as this vector, but it's only half as long? How would we do this? We want a vector same direction as R1, but half as long. What do you think we'd do? Yeah.
So you cut the distance in half, so you know the length of the hypotenuse, and then you solve for the sides.
That's not, so cutting the, yeah, so if we, so you're saying work back you want. There are lots of vectors that have that magnitude though. So that's not, yes?
You would just multiply R1 by 1/2, because the 1/2 is just a scalar. You can multiply vectors.
You can multiply a vector by a scalar. And so what we want to do is take the scalar 1/2 and multiply it by R1. And what we get is 1/2 times 2.5, 0.3 minus 2 meters. And we did, the way scalar multiplication works is you multiply each component by 1/2. And so what we're going to get is 2.5 over 2, which is 1.25, 0.3 over 2, which is 0.15, negative 2 over 2, which is negative 1 meters. And this could be any number. And let's make sure it's really, really, here, let's get back to my, okay, so let's calculate the magnitude of our new vector. Now, notice that we told the computer to calculate the magnitude that, well, let's just do it this way. Or we could actually simplify our lives. Let's actually tell the computer to make a vector. That's our original vector. It was 2.5, 0.3, negative 2. And R2 is going to be 1/2 times R1, so scalar multiplication. Let's print R2 and see, and since we're printing lots of things, let's tell it to write something there for us so we know what we're printing. That's what we got. Now let's find the magnitude of this new vector R2. Now, we could take the square root of the sum of the squares, and you might want to do that to convince yourself it's right, but we can also just ask the computer to do it for us. So we'll say print, or let's say, well, R2 magnitude is just the magnitude of R2. And we'll print the magnitude of R2, and we'll find out that it's 1.6077, which is indeed half of that. So multiplying the vector by the scalar 1/2 did indeed give us a vector that's half as long. About that. How would we make a vector that's the same length as R1, but it points in the opposite direction to R1? Yeah, we just multiply it by negative 1. So minus R1 is minus 1 times R1, which would be minus 2.5 minus 0.3. That's a 3. Minus plus 2 meters. And does that make sense? This should be a vector that starts here and goes to there, and it go 2.5 meters in the negative x direction. That makes sense. We have to go down just a little in the y direction, and we have to go in the plus z direction to get to here. So that makes sense, right? So multiplying by minus 1 reverses the direction of a vector, and a vector is typically represented in diagrams by an arrow with its tail starting somewhere and going somewhere else. So if we have x and y, this would be an arrow representing a vector, and z is out of the board. The specter's in the xy plane, so this might be 5. So we'll use arrows to represent vectors. Okay. So what else can we do with useful? Well, sometimes we have a displacement from someplace to someplace else. So suppose we want to start here and go to here. What do you think the vector that starts at this location and goes to our new location is? This is called relative position. So we'll call this location 1, we'll call this location 2. This is the position of location 2 relative to 1. So what is this vector approximately? Well, is the x-coordinate positive or negative? Okay. So this vector is going to be negative. What do you think? Guess. Estimate. Estimate. 2 meters? More like 1, 2, 3, 1.4. It's okay to guess. It's okay to estimate. Estimates are good. What's the y coordinate of this relative position? 0. And z? 0. So now we'd like to get the position of point 2 relative to our origin. We know the vector that goes from here to here. What if we just added that vector to it and got to here? So we'll call this vector delta r. It means delta means a change. And so the vector r2 is going to be the vector r1 plus this relative position vector delta r. So that's going to equal 2.5, 0.3 minus 2 meters plus negative 1.400 meters. And to add vectors, what do you think you do to add vectors? Right, exactly. You add the x components, you add the y components, you add the z components. So the result is going to be 2.5 minus 1.4 is going to be 1.1, 0.3, negative 2 meters. So vector addition. And likewise, to subtract vectors, you would subtract component-wise. So let's talk about how to do this graphically. Now, it's actually kind of tough to draw in 3 dimensions. This is one reason we want this 3D computer environment, so that we can actually draw arrows in 3 dimensions. But if we did this in 2 dimensions, if we say here's our origin, here was some vector r5, we're adding to it some vector R6. The way we add addition is we put the tail of the vector we want to add to this vector at the tip. So the tail of R6 at the tip of R5. So tail to tip. And what's the sum? Well, the sum is that vector. So this is R5 plus R6. So let's call this actually, so we can do some algebra, let's call this guy R7. So we have that R5 plus R6 R7. So can we rearrange this? So vector algebra mostly works the same way as ordinary algebra. So addition, subtraction, that's good. One thing that's not defined for vectors is dividing by a vector. You can't put a vector in a denominator because it isn't clear what that would mean. But we can rearrange this to say R6 is R7 minus R5. So it looks like this is R7 minus R5. This is important because vector subtraction turns out to be one of the things we do all the time. Because if things are moving, they're at one location, they're at another location, well, we want to find out the displacement between them. And so it looks like to subtract vectors graphically, what we do is we draw R7 and R5 with their tails together, and then we draw R6 going from R5 to R7. If we think of this as the final location, and this is the initial location, we draw it. So subtraction, tail to tail. Another way to do subtraction is to think of what do you have to add to R5 to get R7, and that's R6. So you can always add the negative vector. So these things ought to be consistent. All right. Let us let's take a minute. And so this is a very low-tech version of using clickers. So what I want you to do to answer these questions is to think about it for a second and then just hold on to your answer. Now in this case there are 9 possible things, so you might need 2 hands. But what I want you to do is take just a minute to think about this. Talk to your neighbor. So you have 1 minute to talk to each other and decide what the answer is. There we go. All right, you ready? Hold up some number of fingers. You can just, wow, everybody says 2. And you are exactly right. So if we multiply a vector by a positive scalar, we change its magnitude, but not its direction. Awesome. Let's see what the next question is. If D is a negative scalar, which green arrow represents the direction of the vector dA. Are you not talking because it's obvious, or you're not talking because you Okay, so you ready? What's the answer? Fingers. 4. Yes, if you multiply by a negative scalar, then all the components, the signs of all the components reverse, and so the vector goes in the other direction. Awesome. Now, it would be very nice to have, it would be very useful to have a way of writing a vector that we know how to get the length, we know how to get the magnitude. We just take the square root of the sum of the squares of all the components. So that's the magnitude. It would be nice to have another piece that's just the direction. And so there is a thing like that, and it's called a unit vector. And so if we have some vector A is -3, 2, 4. What's the magnitude of A? Okay, you are going to need devices for calculating things with numbers in lecture and recitation, so bring a calculator. If you want to use your phone, that's legal. So what calculation do we do to get the magnitude of A? Sum of the squares and then square root. Okay. So we want this, we want -3 squared plus 2 squared plus 4 squared. Let's make this a position meters. Which is equal to, somebody got an answer? 5.39 meters. So it'd be nice to just be able to multiply this by something and get this vector back. And the thing that we multiply by is called a unit vector. So a unit vector is a vector whose magnitude is 1. And that means you can multiply any scalar by it and it doesn't change the direction. And so to get a unit vector, we write a unit vector So a unit vector, we put a little hat over it, and this is pronounced a hat. And it's just equal to the vector A divided by its magnitude. And this is useful because if we rearrange it, we're going to find that since the magnitude of A is a scalar, it's okay to divide by it, right? This is a single number. It's not a vector. If we rearrange this by multiplying both sides by magnitude of A, we get that the vector A is equal to its magnitude times this unit vector A in the direction of A. So let's figure out what this is for our vector. A hat is going to be -3 to 4 meters divided by 5.39 meters. So what are the units of this unit vector going to be? They do cancel. They cancel. So a unit vector has no units. So let's say A is a vector, -3 to 4. We'll say A mag is the magnitude of A, and A hat is just going to be A divided by the magnitude of A. And now let's print A and the magnitude of A and A hat, which is so you can see that I'm lazy and don't like to use a calculator. Okay, so this unit vector came out to -0.557, 0.371, 0.743, no units. In a unit vector, could any of the components ever be bigger than 1? What's going to happen if you square them? Yeah, so all the components have to be less than or equal to 1 in a unit vector. Okay, and that's one way to check that you've really got a unit vector is by looking at the components. Now let's just make sure that works by printing the magnitude. We'll call variable A hat. Magnitude of A hat is the square root of, well, we'll just say, we'll let the computer do it, the magnitude of A hat. Print that. And the magnitude comes out to 1. This is good. The magnitude of a unit vector better be 1. So now once we've got this unit vector, we can make all the vectors we want in the direction of A. All we do is multiply by 3 to get a vector of magnitude 3, or 20 to get a vector of magnitude 20, or whatever. So we've got... Now there are 3 quite special unit vectors. And they have special names. So, what do you think a unit vector would be that points along the x plus x-axis? What would the components of a unit vector that points along the x-axis be? So what's the y component? 0. What's the z component? And what do we have to do to make the magnitude of this thing 1? So when we square all the components and take their square root, it better come out to 1. So what does this number need to be? It needs to be 1. Okay. So that's a unit vector along the x-axis, and it is called, as a special name, it's called I hat. And it's a vector along the x-axis. Okay, the unit vector along the y-axis is going to be what? 0, 1, 0. Because if we square these things and take the square root, its magnitude is going to be 1. And k hat is going to be 0, 0, 1. Now, in a previous course, you might have seen vectors written as scalars multiplying unit vectors. So our vector A could be written as a negative 3 times I hat plus 2 j hat plus 4 k hat. So that would be a negative 3 times 1, 0, 0 plus 2 times 0, 1, 0 plus 4 times 0, 0, 1, which is indeed going to come out to Now, we're not going to use this notation in this class because A, it's cumbersome, and B, it makes it look like a vector is composed of 3 different things added together, and that's not right. A vector is one thing. It just has 3 pieces. Okay, there's one more thing we need to do with, so questions so far. It's okay to have questions. Okay. One more thing we need to do with vectors, and that's talk about what it means for one vector to be equal to another vector. So remember our vector R1 going from here to there. What would it mean for some other vector to be equal to that vector? What would it mean for some vector to be equal to our vector A? So if we have our vector A that's negative 3 to 4 meters, and I say there's a vector B that's equal to vector A, what do we know about vector B? Same magnitude, same direction, that's exactly right. What about all of its components? So if we write B, the components must be the same. So B must be negative 3 to 4. So this equation, this vector equation, is really a very compact way of writing 3 separate equations. What it really says is that if we have some vector A who's equal to A sub x, A sub y, A sub z, these things here we call components, right? And a component of a vector is not a vector, it's a scalar. That must mean that we have B sub x equals A sub x, so if B is B sub x, B sub y, B sub z, so if B sub y is A sub y, B sub z is a sub z. Okay, so equality of vectors means all the components have to be equal, the directions have to be equal, the magnitudes have to be equal. This is going to be really important because if we're trying to interactions of objects, and we're talking about forces which have magnitudes and directions and velocities which have magnitudes and directions, then one vector being equal to another vector means that all the components are equal, the magnitudes are equal, and the directions are equal. Super important. Okay. Now there's one other thing we can do with vectors, and we need to be able to do it, but we're not going to stress out over it a whole lot. Most of the time when you're walking around in a three-dimensional world, you're much more likely to have a ruler than you are a protractor. So you mostly know distances and not angles. And in fact, in a 3D world, it's actually really tough sometimes to figure out what angle you're working with. So if you think vectors are sines and cosines, that's kind of a restricted view. But it is sometimes useful to be able to get angles to axes from vectors. So here we go. So here we have a 3D coordinate system, and the labels aren't very big, but this is x, and that's y, and that's z. And here's a vector which looks like it's in the xz plane. Now this will take a little getting used to. The plane of the ground in our coordinates is indeed the xz plane. And we would like to be able to write a unit vector in a particular direction in terms of angles with the axes. And it turns out the way this works is that some vector a hat can be written as in terms of cosines of angles an axis. We use direction cosines because that way you don't get mixed up as to whether you're using sine or cosine, and so it works like this. It could be written as cosine of the angle with the x-axis. The y component is the cosine of the angle with the y-axis. What does that mean? Well, here's our... Is the angle with the x-axis bigger than 90 degrees, less than 90 degrees? We're always going to take the smaller ones, so there are two possible ways. We could go around this way, we're going to go around that way. So it's this, that angle is the angle between this vector and the x-axis. So that is more than 90 degrees. And that means that the cosine of an angle that's bigger than 90 degrees is positive or negative. 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 So that makes sense because the x component of this vector is negative. Okay? All right. What's the angle this vector makes with the y-axis? It's in the xz plane. So it's in the xz plane. The y-axis is perpendicular to the xz plane, 90 degrees. So this is theta sub x. That is then theta sub y. What's theta sub z going to look like? bigger or less than 90 degrees. That's the so that's what those angles mean. And using cosines means we're not going to use the wrong trig function. These are called direction cosines. So let's consider, let's work in 2 dimensions for a minute because this makes our life simpler. If we have a vector B and we know that this angle is 30 degrees and we want to get a unit vector in this direction, what would we do? So B hat, what's the angle this vector makes with the x-axis? Okay, so first of all, what is the angle? Where's the x-axis? There, positive x-axis. Positive x-axis. So that's 90, and that's 90 minus 30. This must be 60. And so this whole angle is indeed 150 degrees. What's the angle this vector makes with the y-axis? Plus y-axis. Yep, 60. So this is our 60 degrees here. So cosine of 60 degrees. What's the angle it makes with the plus z-axis? Okay, well, it's either 0 or 90. Which is it? So here's the z-axis coming out of the board. So thinking in 3 dimensions is a little unfamiliar, isn't it? Yeah. But we want the angle between this vector and this axis. The angle is 90 degrees, isn't it? The cosine of 90 degrees is 0, so the component ends up being so. Now, we're not going to. There'll be times when we really will need to use this, and we'll practice it a little, and then we'll refresh ourselves with it. But that's the main message here. So what happens today in recitation? It's a little unusual. What we're going to do, this is our first day, we're going to these vector operations, and we're going to practice figuring out not only how to subtract vectors, how to add vectors, how to multiply a vector by a scalar. You can do that. We're going to practice figuring out when we need to do it, because that's the key thing. And you'll find in Canvas that there's an introduction to the Python, the little tutorial that is going to be kind of fun, I hope, and you should work on. There are no labs this week. If you would like help going through some of the introductory material, someone will be in room 204 during our regularly scheduled lab times, so office hours. And if you have the Monday lab, which didn't happen, Friday morning at the same time as the Monday lab. Okay, so time to come get help, use a computer, work on this, whatever you want. I will see you at 2? 2. See you at 2. Bring a calculator. Come ready to work.